Good afternoon, everyone. Is my screen visible?
Yes, ma'am.
Yes, ma'am.
Okay. Are the slides visible?
Yes, ma'am.
So let's start our today's session. So good afternoon, everyone. Today is our problem solving session fourth, and I am your TA Vidushi, and my PMNF ID is 0602607. So first start with Raman spectroscopy. So what do you understand by the Raman spectroscopy? It is a technique which is used to observe vibrational, rotational, and low frequency modes in a system. Basically, in this, there are two types of scattering: elastic and inelastic scattering. There can be elastic and inelastic scattering. When an incident photon of energy h mu raises the molecule from a vibrational state to one of the infinite number of virtual states located between the ground and first electronic states. Like here, these are different energy levels. When a molecule is excited to a high energy level, and suppose with a frequency of mu I, and then it relaxes back to the ground state with a frequency of mu s, and if it relaxes to the same energy level, then this type of scattering is called as Rayleigh scattering. In Rayleigh scattering, basically a molecule is excited to a higher energy level or a virtual state, and then it relaxes back to its original state, and the photon is scattered elastically, leaving its original energy. So this type of scattering is a Rayleigh scattering, and in Rayleigh scattering, it is an elastic scattering. While another type of scattering is called stock scattering. What happens in stock scattering is that when a molecule is excited to any virtual state or any higher excited state, then it relaxes back, like here, the molecule is excited, then it relaxes back to a state lower than its original. Like from here it started, so it relaxes back to a lower state. And this type of scattering is stock scattering, and this energy is given by h mu minus delta E. Here this will be the frequency of the incident radiation, and this will be the frequency of the scattered radiation. So here the energy will be h mu minus delta E. Whereas in anti-stock scattering, when a molecule is excited to a virtual state, then it relaxes back to the ground state of higher energy than that of the incident. So here the energy will be h mu plus del E. This is anti-stock scattering. The stock scattering is an inelastic scattering. Now here, this spectrum is of the Raman spectrum of the CCl4. In this, we observe like there is stock line, Rayleigh scattering, and anti-stock line. So the line that is left of the Rayleigh line and has like here it's a Raman shift on the x-axis, and on y-axis it instance is the intensity. So the line that is to the left of the Rayleigh scattering and which has a lower value of the wave number, are the Stokes line, and the line that is to the right of the Rayleigh scattering and has a higher value of the wave number is anti-Stock line. So you can easily remember Stock and anti-Stock line by that. In Stock line, if a molecule is excited to a virtual state and when it relaxes back, it will come to the lower level than that of the incident. And in Stock line, it will be to the left of the Rayleigh and will have low value of the wave number. Whereas in anti-Stock line, when you excite a molecule to a higher virtual state and then it relaxes back to a higher level than that of the incident, that will be anti-Stoke line and it will be to the right of the Rayleigh line, and the wave number value will also be higher for the anti-Stoke line. The positions, so what do you understand by the term now? Raman shift. Like here in x-axis we denote by Raman shift. So what is Raman shift? The position of Raman lines are generally expressed in terms of Raman shift. So this is the equation: delta wave number is equals to wave number of scattered minus wave number of incident, where these two are the wave numbers of the source or incident radiation and the observed scattered line respectively. And it is also obvious that the Raman shift of the Stoke line would be positive while that of the anti-Stoke would be negative, because you know that in Stoke line the molecule after excited relaxes back to a lower level, so it will be positive Raman shift for the Stoke, while for anti-Stoke it will be negative. So basically in this you just have to remember that for the Stoke shift it will be denoted by, like, the Raman shift value for the Stoke shift will be this, where this is of the incident and this is of the scattered. So this is the value of the Raman shift in case of Stoke line, while for anti-Stoke the value of Raman shift will be, so you just have to remember these two formula. This is for the Stoke line and this is for the anti-Stoke line. Anti-Stoke line. So now moving to questions. Which type of interactions between the electromagnetic radiation and matter is studied in Raman spectroscopy? Is it transmission, absorption, reflection, or scattering? So, what will be the answer?
Scattering.
Scattering.
Yeah, it will be scattering. Now, which of the following depicts the correct order of intensity for the below transitions? Relay, anti-stock, stock. Like, out of these, what will the correct order of the intensity? Like, which will have high intensity? Relay, anti-stock, or stock?
Third one.
Third one.
Raleigh.
Yeah, it will third one. Like, you know that for stock and anti-stock, for the stock, when a molecule is excited to a high vibration state, then relax it to ground state of lower energy. By that of anti-stock, if a molecule is excited to a higher virtual state or any virtual state, then when it will be relaxed back, it will have relaxed back to a higher level than that of the incident. So that's anti-stock. So therefore, stock will have higher intensity than anti-stock, and then Rayleigh will have the highest intensity out of these three. Uh, Now the next question is, overtones and fingerprint region are observed at near IR, mid IR, or far IR. So in which region is overtones and fingerprint observed?
Mid-IR.
Mid IR. Why? Like what are basically overtones? Like in IS spectroscopy, you have studied about overtones. What are overtones?
The frequencies after the fundamentals.
No. Please repeat.
Frequencies after the fundamentals.
Okay. So basically, what are overtones? Overtones are a result of absorption of light at higher energy level than that of the fundamental frequency of the molecular vibration. They are generally observed in the near IR region. That's around 4, uh, in the near IR region. And what are fingerprint regions? We discussed earlier in earlier sessions. Like in IR, there are function group region and the fingerprint region, and the fingerprint region are observed in 1400 to 600 centimeter inverse. So the correct answer will be near IR. So the next question is, according to Hooke's law, which of the following will have higher force constant value out of acetylene, ethane, and ethylene? So what is Hooke's law?
P is equals to minus kx.
Okay, and we also know this formula.
Root K by M.
Hmm. Yeah, it's root k by mu, where mu is the reduced mass, k is the force constant. So in the question they are asking which will have higher force constant, whether it will be acetylene, ethane, or ethylene. You know acetylene is
Ethylene will have the highest.
uh, you're not audible. What are you saying?
Ethylene. Option C.
Ethylene.
Yes.
Why ethylene?
Triple bond is present, so
Ethylene is not triple bond. Acetylene is triple bond.
yes, ma'am. Sorry.
Acetylene is triple bond. Ethane is C2H6. The single bond. CH3. CH3. This is ethane. While ethylene is CH2 double bond CH2. So now what will the answer? What will the answer? Like you just have to tell which will have higher force constant. Now you know that. Like acetylene is two carbon
Ethane.
atom. Pardon?
Ethane, ma'am.
Ethane. No. Like what do you understand by force constant?
Acetylene has higher force constant, isn't it?
It will be acetylene. Like what do you understand by K? K is force constant. Force constant means how a bond strong, like how strong a bond will be. So like out of these three, like out of triple, single, and double bond, which will have a stronger bond? Triple bond. So the K value or the force constant value will be higher for acetylene. So that's why answer will be acetylene. So there K is the force constant, or it's like it tells about the bone strength, like how stronger a bond is. So just remember for force constant value for triple bond will be higher then it will be double bond, and then it will be single bond. This is the order for the force constant. So in acetylene there is triple bond, so the answer will be acetylene. Because if you will just see about mu is reduced mass. It's M1 M2 upon M1 plus M2. If I will ask you about like which will have a highest touching frequency out of these three, so what will be the answer? Like out of acetylene, ethane, and ethylene, which will have a higher value of mu or stretching frequency or frequency like normally. What will the like who will have higher value of mu?
Ethane.
It will be
Acetylene.
acetylene. Yeah, because it is directly proportional. So if acetylene has a higher force constant, so the value of mu will also be higher for acetylene. Now to the next question. Aromatic CH stretching falls in the range. Is it 3100 to 3000, 3300 to 3200, 3000 to 2900, 2650 to 2500? Like what will the range?
Second option.
Second option. Anyone else?
First option, ma'am.
First option. So the answer will be the first. 3100 to 3000. Actually, you all have to remember the value of like CH stretching, carbonyl, OH, NH. This you'll this all values you have to memorize. Like for OH stretching, it will be near about 3200, 3300. Like for the CH, it will be near about 2900 centimeter inverse. For nitriles or like triple bond, it will be approximately 2200. For carbonyl, it will be generally 1700, but it will change. Like if it is ester or it will be aldehyde ketone, then the value will be different. And then it's come like from less than 1400, it's the fingerprint region. So you all have to memorize like for different functional, like for OH, for ester, for carbonyl, aldehyde. Now the next question is IR spectroscopy cannot distinguish between cis and trans isomers, position isomers, tautomers, or enantiomers.
Tautomers.
Tautomers, okay. Like tautomers, like keto-enol tautomer, keto and enol. So in keto form, like in the keto form, it will have a different frequency, like different IR value, or the function will have like it's CO, so it have a different value. Like in the enol form, it will have a different value. So IR can distinguish between them. So out of these, IR can't distinguish between cis or trans, position or enantiomers.
Enantiomer.
Enantiomers, yeah, it will be enantiomers. Because in cis and trans isomers also, like this is cis, this will be cis form, as and this will be the trans form. So this is trans and this is cis. So IR spectroscopy cannot distinguish between enantiomers. Now the next question. See, a molecule has a force constant of 1840. The vibrational stretching frequency is 1755, 2034, 2134, and 1965. You have to calculate the stretching frequency and the value force constant is given. Just solve and tell me the value. You know the formula also, right? How we can calculate the vibrational stretching frequency. So what is the formula?
U is equals to 1 by 2 pi root of A by nu.
Yeah. So just put the value of the force constant. So what would the stretching frequency? Like you know this formula. So what will be the answer? So what will the answer? Kartikeya, Deepak. We already have, I think, in third session we have solved the same question. So what will be the answer? You just have to put the value. You know the value of force constant is given, that is 1840. You have to calculate the value of this stretching frequency. Pi, you know, it's 3.14. Reduced mass, you have to calculate. It will be m1, m2 divided by m1 plus m2.
It option B.
Option B. Okay. So what's the value of mu? Reduced mass. Like for CO molecule, carbon monoxide, it will be nearly 11.38 into 10 raised to minus 27. You know mass of the carbon is 12 and like oxygen 16. So by solving you will get mu value this. So substitute it in the equation here 1 upon 1 divided by
11.38 into 10 power minus 27.
yeah, that's the value of reduced mass. So just put this value of reduced mass in this equation.
2.01 into 10 power 5.
Okay.
Then the answer is like
Yes,
2023. So while calculating, the answer comes like 2023. But it is not in their option. I put the same values, but
it's 2023.
yes,
Okay, I will just check my answer.
Ma'am, I got 2010, ma'am.
2010. Okay, let me check once. It's 1 divided by 2 into 3. 11.38. Like after solving this, it will be 1 divided by 2 into 3.14 under root 161.68 into 10 raised to 27. So it will be under root 1661.6871. So what's the value of this under root? It will be approx 12.71. 12.71 divided by 6.28. It will be approx 2.02. So how much value you are getting?
Yes, ma'am, same.
Yeah, this will not be the answer. So because how you will solve it, it will be like 6.28 multiplied by 12.71. Like after the root of this is 12.71. So it will approx 2.02. Now the next question. In which region of IR every molecule shows its characteristic spectrum? Near IR, fingerprint, far IR and functional group. So what will be the answer? In which region of IR every molecule shows its characteristic spectrum? Near IR, fingerprint, far IR or functional group? The answer will be fingerprint region. Now the next question is detection of homonuclear diatomic molecules can be done through IR, Raman, microwave spectroscopy. So
Hello, hello.
yes,
Ma'am, can you tell the previous numerical, what is the final answer of that exact
so it will be 2023 sir.
numerical?
Actually this is wrong.
Ma'am, screen is not visible, ma'am. Ma'am, screen is not visible.
Screen is not visible.
Yes, ma'am.
Just a second.
It's visible, ma'am.
Like, is it visible?
Yes, ma'am.
Actually, from my side, okay. So
Uh,
the next, so the next question is detection of homonuclear diatomic molecules can be done through IR, Raman, microwave spectroscopy. So what are homonuclear diatomic molecules? Like H2, N2,
O2.
O2. Yeah, correct. So by which technique you can detect it? Like IR, Raman, or microwave?
Microwave.
Mic. Okay. Why not IR and Raman?
Microwave is rotational spectroscopy, ma'am.
Microwave is inactive for
You're
actually
not
microwave is inactive, right? For diatomic molecules.
okay. Like why? Like just
So
tell me
can
first.
we dispose? I mean,
Like, actually, you're not audible. What are you saying? Can you repeat?
ma'am, microwave spectroscopy it is actually inactive for homonuclear diatomic molecules, right?
Okay. Okay.
So so can we detect it with that? Is it possible? I don't know. I was asking
Actually,
that.
your voice is breaking. I just only heard microwave
Okay.
is inactive for homonuclear. That's what you were trying to say?
Yes, microwave is inactive. So can we detect it with microwave? Is it possible like that?
No, it can't detect. Microwave can't detect. Like in IR, you know that for IR active, there should be change in dipole moment. But here, in case of
Hmm.
homonuclear, there will like dipole moment will not be changed. So IR can't detect these molecules, but Raman can. So the answer will be Raman spectroscopy. Actually, do you know this principle, mutual exclusion principle?
No,
Actually,
ma'am.
according to this principle, in a molecule with a center of symmetry, like just take an example, CO2. As in this molecule, center of symmetry is present. So for that molecule, those vibrational modes which are Raman active are IR inactive, and that in which IR active modes are Raman inactive. So that's mutual exclusion principle. Like for IR, those molecules which are IR active will be Raman inactive, and the molecules which are IR inactive are Raman active.
Ma'am, I am unable to see screen, madam. Presentation screen.
I don't know, like from my side, the screen is visible. I don't know why. Actually, the screen is shared
It's
from my
actually
side.
visible, ma'am.
It's visible. Like for, I
Yes,
think
it is visible.
it's. So who was saying like the screen is not visible? Pala Vasu.
What? Yes, ma'am. Once I log out and I will rejoin. Ma'am.
Okay.
Okay.
So according to mutual exclusion principle, just remember that If in a molecule there is center of symmetry, then IR active will be Raman inactive, and IR inactive will be Raman active. Only if center of symmetry is present in that particular molecule. Inactive will have Raman active. So now H2, O2 and N2, they have center of symmetry like here. Center of symmetry is present in these homonuclear diatomic molecules. So they are Raman active. As they are IR inactive, so they will be Raman active. If you just take an example of CO2, like CO2 here, it's a triatomic molecule. There are three atoms, C and two oxygen. So this is triatomic molecule. So in this, of the three fundamental vibrational modes, only the symmetric stretching mode is Raman active. So what are the three fundamental vibrational modes? Like it can be stretching, like symmetric stretching, asymmetric stretching, or bending. So out of that, only the symmetric stretching mode is Raman active. And in bending mode, the bond length will remain constant. Thus, there will be no change in polarizability. While in antisymmetric mode, there will be increase in polarizability of one carbonyl bond, which will be neutralized by the decrease in polarizability of the other. Thus, the two modes will be Raman inactive. But there is definite change in dipole moment, and consequently, they are IR active. So the reverse is case for the stretching. That's why in case of symmetrical stretching, it is Raman active. Or like in simple terms, if I will tell you, like what are the three modes in the CO2, it will be like symmetrical stretching, anti-symmetrical stretching, and bending. So basically what happens in the symmetric stretching, like the bond is stretched in the same direction. While anti-symmetric, the bond is stretched in different directions. So here is symmetrical stretching, it is Raman active. And in asymmetric stretching, it means the stretching is in different direction. If here from one side it is stretched, so in here different direction it will be stretched. So in that case, there will be increase in polarizability at one CO bond, which will be neutralized by the decrease in polarizability in the other. Therefore, it will be Raman inactive. While in case of bending mode, it will also be Raman inactive. Why? Because in bending, the bond length will remain constant and there will be no change in the polarizability. So is it clear? Like here, just remember this table for CO2. For symmetric, Raman active and Dyer inactive. While the bending and asymmetric stretching, it will be Raman inactive and iron active. So this is the mutual exclusion principle. It is only applicable if the molecule has center of symmetry. Just remember it. Only with center of symmetry. Is it clear?
Yes, ma'am.
So the correct answer will be Raman spectroscopy. So the next question is, molecules having like containing the vibrations without center of symmetry are like those molecules in which there is no center of symmetry. Will it be iron active or inactive? Or Raman active or inactive? Now you know. Like
Both IR
Hmm.
and
both IR and
Fourth option.
first option. IR active and Raman inactive.
Yes, ma'am.
both IR and active.
Okay, anyone else?
First option.
First option. It will be both
First
Raman
option.
and
First
IR
option.
active. It's saying without center of symmetry. In which molecule there is no center of symmetry. Because you know that if the molecule has center of symmetry, if it have, then for IR active it will be Raman inactive. Just a second. IR active, then it will be Raman inactive. This was for if a molecule has center of symmetry. Now they're asking the molecule do not have center of symmetry. So in that case, both Raman and IR will be active. Because for IR active, there should be a change in dipole moment. Just remember that. So now the next question is the force constant for the four diatomic molecules are given below. So the value of force constant K is given for N2, HCl, CO and F2. Which of the four molecules has the highest vibrational wave number? So what will be the answer?
F2.
And F2. Why F2?
It's
Wave number
directly
is directly
proportional.
proportional to force constant.
Okay, but see these are like this is heteronuclear diatomic molecule, na? And it like N2 F2 are homonuclear. So just calculate according to reduced mass as well. So masses will be different for all molecules because you know that frequency depends on both force constant and reduced mass. So take both into consideration. So now just tell me
CO, ma'am.
HCl. Oh, I'm sorry, you are telling CO. Okay. Just tell me like what will the wave number for N2 HCl and COF2 respectively? Just first solve for N2. You know this formula. So now calculate the wave number for N2. Force constant is given, it's 450. Reduced mass you can calculate M1 M2 upon M1 plus M2. Like what will be for the HCl, CO and F2? Just calculate wave number for all of these and tell me the values. So what's the wave number for HCl, CO, F2? Has anyone calculated it? Like the mass of nitrogen, hydrogen, chlorine. You can easily calculate the value of reduced mass. And then substitute the value in this equation and calculate the wave number. Force constant is already given in the question. Is anyone solving it? Deepak, Arun, who else are there?
Yes, ma'am.
Like, what will the value of the wave number for N2 or like out of these? Like, have you solved it? You just have to substitute the value. Everything is given. Vaishnav.
1.27 for N2.
For N2, what will it will be?
1.27.
1.7 in
1 point.
7 into 10 power minus 27.
Okay, and for HCl, HCl, COF2.
Hello.
Yes.
Ma'am, I have a small doubt, ma'am. In the M1 plus M2 by M1 M2, M1 for N2, I have to take what value, ma'am? M2, what value?
Like for M1, M2, what do we have to take? What are you saying?
Yes, ma'am. Yes, ma'am.
Like if you're taking for HCl, mass of
Okay.
hydrogen is 1, and for Cl,
Okay.
it's 35.5. But that's in AMU, so you have to convert it by multiplying by 1.66. I think we have already.
Yes, ma'am. But for in N2 case, both nitrogens I have to take M1 and M2.
Yes, like for like
Okay.
yeah.
CO 4.48.
For CO it is
4.48.
4.48. Okay, and for HCl and
No,
F2.
actually, we did see CEO in the last question, right?
Cu is the so now out of these HCl will have the highest wave number. So take your time and do the calculation and just match it. So out of these HCl will have the highest wave number. I will not solve it like we have already done multiple times now. So just remember this. So now what is the order of the vibrational frequency for CCl, CBr, CC, CO and CH? So what will be the answer? What is the order of vibrational frequency?
CH, CC, CO, CCL, CBR, ma'am.
Yeah. Why?
Vibrational frequency is inversely proportional to reduced mass, ma'am.
Yes. So now it's hydrogen. So reduced mass will be less.
For hydrogen, ma'am.
Yeah. Comparative like Br is a like it's hydrogen, carbon, oxygen, Cl and Br. So you know that mass of hydrogen is less. So stretching frequency will be higher. So now the Raman intensity depends on intensity of source, concentration of Raman active group, polarizability of molecule, all of the above. So on what factor Raman intensity will depend? On the intensity of the source, concentration of Raman active group, polarizability of the molecule, or all of the above.
All of the above.
All of the above.
Yeah. So it depends on intensity, concentration, polarizability, all three. Molecule that obeys mutual exclusion principle is CNS, CO2, HCl, or HC triple bond CCl. Now we have already discussed, I think, in 2 3 slides
CO2.
back, it will be CO2. So, what was mutual exclusion principle? That if a molecule has a center of symmetry, then a Raman active will be ion inactive, or ion active will be Raman inactive. The answer will be CO2. Which of the following cannot be conserved during Raman scattering? Total energy, momentum, kinetic energy, or electronic energy? It cannot be conserved.
Electronic energy. Is it? uh,
No, it will be kinetic energy. Next question. Using radiation of wavelength 4 into 10 raised to power 3
ma'am, can you say how kinetic energy can be conserved? Just
so Raman
brief
scattering,
opinion.
okay. Raman scattering is elastic or inelastic?
Inelastic, right?
So just tell me, it is elastic or inelastic?
Stokes and anti-stokes we get for inelastic, right?
Yeah. So it is also inelastic scattering, na?
Yes.
So in inelastic scattering, the kinetic energy is not conserved. Everything like total
Okay, ma'am.
energy, momentum is conserved. Is it clear?
Yes, ma'am. Yes, ma'am.
Just remember that Rayleigh scattering. What was Rayleigh scattering? Like if a molecule is excited to higher energy level and then it relaxes back to the same vibrational level that of the original state. So that's Rayleigh scattering, and it will be Rayleigh scattering will be elastic scattering. While inelastic scattering are the Stoke. Like in Stoke, if a molecule is excited to any virtual state and then relaxes back to lower vibrational level. So that's inelastic scattering. You just have to remember Stoke. What do you understand by Rayleigh scattering, Stoke line, or anti-Stoke line? And always remember that Raman scattering is inelastic. So in that case, kinetic energy is not conserved. So the next question is using radiation of wavelength, it's Armstrong. 4 into 10 raised to the 3 Armstrong. The first Stoke line appears at spacing 350 centimeter inverse from the Rayleigh line. Calculate the frequency of the first anti-Stoke line. So what will be the answer? Like frequency of the like the wavelength of the incident is given, like incident radiation is given, it's 4 into 10 raised to the 3 Armstrong, and the spacing is also given. But what is spacing like here? It is Raman shift. So you just have to calculate the frequency of the first anti-Stoke line. We have already discussed, like for the Stokes line, the value of the Raman shift will be, and for the anti-Stoke it will be, this for the Stoke, and this was for the anti-Stoke. So now you know this is the wavelength of the incident radiation, and this is the Raman shift value, that is 350. So what will the frequency of the first anti-Stoke line? For anti-Stoke, you know this formula. Raman shift is equals to frequency of scattered minus frequency of incident radiation. Incident radiation and scattered. Like here, see the wavelength is given of the incident radiation is 4 into 10 raised to the 3 Armstrong. So here we have to convert this into wave number. So what's the relation between wave number and the Wavelength?
C by lambda.
Like I am asking for the wave number and wavelength.
Inverse
1 by
relationship.
lambda.
Wow.
Huh?
1 by
1 by
lambda.
lambda, yeah. So just convert it into wave number. One Armstrong is 10 raised to 1 minus 10 meter. So just convert it into centimeter. So it will be 10 minus 8. So what will the value wave number? After solving this, it will be 2500. So then just put this value in this equation. You know what's the value of Raman shift? It's 350. And this frequency you have to calculate for the anti-stock line. So it will be 25350 centimeter inverse. Is it clear? Basically, in this question, incident radiation wavelength was given and value Fermi shift was also given. You just have to calculate the frequency of the first anti-stock line. And you know that for the anti-stock, Raman shift is given by difference in the scattering frequency and the incident frequency. So you just have to calculate the mu s. But here the value was like wavelength, you know that. So just you have to convert earlier it into wave number, then substitute the value in this equation and calculate the value of mu s. Is it clear?
Ma'am, actually, this value, the wave number value, we are getting like 25,000 centimeter inverse. It's not 2,500, I believe. Like when you
Yeah,
do the
it's
calculation,
25,000. Yeah, yeah, it will be 25,000. Like, is it clear?
Yes, ma'am.
So just remember these two formulas. Now the next question is the rotational Raman spectra of 35Cl2. Like for the chlorine molecule, it shows a series of stock lines separated by 0.9752 centimeter inverse and a similar series of anti-stock line. Calculate the bond length of a molecule. So how you will calculate the bond length? I think in previous session we discussed like this type of question. Like we know that I is equals to mu r square, and for that like r is the bond length, so it will be square of I by mu. For that you first have to calculate the value of I. So what's the formula to calculate I? What's the formula to calculate I? I think
H
we
by 8 pi square BC. Are we using that equation?
which equation?
H by 8 pi square.
Correct. We know that B is equals to H upon 8 pi square IC. So from that we can calculate I. I will be H upon 8 pi square BC, and you, like here in the question it is given, it shows a series of stock lengths separated by 0.97. So you know that value of 4B in spacing, it's 0.9752. So what it, the B will be 0.9752 divided by 4. 4. So what will the value after dividing it? It will be near about 0.2438. So now substitute the value of B in this equation to calculate the value of I. It will be I is equals to 6.626 into 10 raised to minus 27 divided by 8 into 3.4 3.14 whole square into B, it's 0.2438 into 3 into 10 raised to 10. So what will the value after solving it? 0. So what will the value? Just solve it. Like what will the value of I after solving? What will be the value of I? Like just you have to divide now 6.626 into 10 minus 27 divided by 8 into 3.14 whole square into 0.2438 into 3 into 10 raised to 10. What will be the value? It will be 1.1438.
1 4.
Yeah, into 10 raised to power minus 38. So now substitute the value in this. I, sorry, R is equals to under root 1.1438 into 10 raised to minus 38. And what about reduced
Ma'am,
mass?
can you hear me?
Yes.
Like this H value.
It's like 6.6 into 10 raised to minus 34, right? But
But we
you
have to
put something
convert
like
into
10.
units now. Like unit, you also have to, like here also, the value of c is 3 into 10 raised to 8 meter per second. But we have to convert it into centimeter. That's why we take by 3 into 10 raised to 10 centimeter. So this will, like here,
Okay.
yeah, here the units will be gram, second inverse, centimeter square. So, but with the value of mu, like reduced mass, just calculate the reduced mass for the, sorry, calculate the reduced mass for Cl2. It will be, what will the reduced mass? Just
1.62,
1?
1.62 into 10 raised to minus 27.
No, this is not correct. Like, what are you taking the values of M1 and M2?
1 and 35.
Mass of chlorine is 35.5, na? So just like here, it's
Oh,
M1 M2 divide by
And
M1 plus,
28.5.
yeah, it will be 2.9. So after solving it, the value will be approx 1 2.90 into 10 minus 23, because the mass of chlorine is 35.5 for M1 M2 both. Like for M1 is 35.5, for M2 is 35.5. But then you have to divide it by Avogadro number also, no? Like 6.022 into 10 raised to 23. After that, the value will be 2.90 into 10 raised to 23. So if you will substitute this value in this, so the value of bond length will be 1.98 Armstrong. So now the next question is, HCl molecule is absorbed at the radiation 2885.9 centimeter inverse by using Boltzmann distribution. Calculate the relative number of four worst vibrational level and the ground level at 25 degrees Celsius. Suppose the number of molecule ground level is 1. So you have to calculate the number of relative number for the first vibrational level. It's not erasing. So how you will calculate it? You know this formula? Like they're asking the first vibration level and the ground level. So it's the relative number for E minus raised to power minus del E by kt, or we can write it as E raised to power minus HC dash by KT, and we know the value of H is 6.626 in 10 raised to minus 34 into 3 into 10 raised to 10 into here HC molecules absorbed at the radiation of 2885.9. So it will be 2885.9 divided by, what's the value of K? It's 1.38 into 10 raised to minus 23, and temperature is 25 degrees Celsius, so we have to convert it into Kelvin by adding 273, so it will be 298. So after solving, the relative number of this vibration level will be 9.245. It's 9.245 into 10 raised to minus 7. So this is the number. Is it clear? Is it clear? Like up to now, is it
Yes,
clear? Okay. So the next question is the fundamental vibration spectrum of CO molecule at a wave number 2138 centimeter inverse, and the line which represent the transition from second to third at a wave number of 2091. So you have to calculate the harmonic constant, unharmonic constant, and dissociation energy. So firstly we will calculate the harmonic constant. Maybe I can take a new slide. Yeah, I don't know why it is not erasing. Yes, so in the question it was given for the transition 2 to 3, the wave number is 2091, and the fundamental vibration spectrum will be at a wave number 2138. So firstly we will calculate the harmonic constant, that is omega e. So here the formula is omega e 1 plus v 1 by 2 plus v minus omega e xc v plus half whole square. So firstly for fundamental, like for first it will be from like It's from 1 to 0 transition, so it will be G1 to 0. So it will be omega E. V will be 1 plus half minus omega E XC. What is omega E XC? Omega E XC is the unharmonic constant. 1 plus half whole square minus omega E 0 plus half minus omega E XC 0 plus half whole square. So it will be 1 plus half, it's 3 by 2. 3 by 2 omega E minus square of 3 by 2, it will be 9 by 4 omega E XC minus, it will be half omega E and then it will be minus, and then it's minus again, then minus minus plus, it will be 1 by 4 omega E XC. So after solving it, it will be omega E minus 2 omega E XC, and for this it was 2138. So it will be 2138. So this is the first equation. Now you know that for the second transition 2 to 3, the wave number is 2091. So similarly, we will calculate for it. It will be 3 minus 2. So, and just directly solving it, it will be 7 by 2 omega E minus 7 by 2 whole square, 49 by 4 omega E XC minus, it will be 5 by 2 omega E minus is 25 by 4 omega E XC. And for this, the value was 2091. So the second equation will be 2091 equals to omega E minus 6 omega E XC. So now you know two equations. 2138 equals to omega E minus 2 omega E XC, and 2091 equals to omega E minus 6 omega E XC. So after equate these two, then you will get 47 centimeter inverse is equals to 4 omega e xc. So from here, what will the value of omega e xc? It will be 47 divided by 4. So that will be 11.75 centimeter inverse. So now you can put this value of omega e xc in out of like maybe in one or two, or like in any equation, like either in one or two. Then after that you will get the value like here 2138 is equals to omega e minus 2 omega e xc, and substitute the value of omega e xc, it's 11.75. So from that you will calculate the value of omega e, and omega e will be 2161.5 centimeter inverse. So you have calculated the value of harmonic constant as well as the unharmonic constant. Harmonic constant and unharmonic constant. Is it clear up to this? Like basically you know this formula, omega e into half plus v minus omega e x into v plus half whole square. So for first fundamental transition, it's like substitute v to 1, then it will be omega e 1 plus half minus omega e xc 1 plus half whole square minus, then v will be 0, omega e 0 plus half minus omega e xc 0 plus half whole square. So from here it will be 3 by 2 omega e minus 9 by 4 omega e xc minus half omega e minus, and like here it's minus, the minus minus will be plus 1 by 4 omega e xc. So after solving it, like half 3 by 2 omega e minus 1 by 2 omega e will be omega e minus 9 by 4 omega e xc plus 1 by 4 omega e xc. So after solving it, it will be omega e minus 2 omega e xc, and the value of the wave number was given to be 2138. So this will be your first equation. Now for the transition of 3 to 2, it will be 7 by 2 omega e minus 49 by 4 omega e xc minus 5 by 2 omega e minus 25 by 4 omega e xc. So for that the wave number was 2091. So it will be 2091 equals to omega e minus 6 omega e xc. So if you equate these two equation, from that omega will be cancel out. 2138 minus 2091, it's 47 centimeter inverse equals to 6 omega xc minus 2 omega xc, it will be 4 omega xc. So 47 by 4 equals to omega xc, and from that omega xc will be 11.75 centimeter inverse. So this is the value of anharmonic constant. So from that, if you will put this value in either in this equation or this equation, then you can calculate the value of omega e. So if you are putting this value in this equation, then 2138 is equals to omega e minus 2 omega e xc, and the value of omega e xc is known that it is 11.75. So it will be final, the value of omega e will be 2161.5 centimeter inverse. Is it clear up to this?
Yes, ma'am.
Okay. So now the last is you have to calculate the dissociation energy also. So I will again take a new slide. So what's the formula to calculate the dissociation energy? So how do you calculate the dissociation energy? it is omega E square divided by 4 omega E XE. Just a second. 4 omega E XE. So substitute the value here. You know the value of omega E and omega E XE. Omega E is 2161.5. 2161.5 centimeter inverse square of, and what's the value of anharmonic constant omega ex? It is 11.75. 11.75. So from here you will calculate the value of dissociation energy. Just remember this formula. Is it clear? Is it clear how to calculate the harmonic constant, anharmonic constant, and dissociation energy? Is it clear to everyone?
Yeah.
Should I repeat it once, or like is it clear to everyone?
Clear, ma'am.
Okay. So I will move further. So the next question is, give approximate positions of characteristics IR bands in the following: CH2, C double bond to CH3, ethanol, CH3, COH, CH3, CO, CH2, CH double bond, CH2. So what will be the IR bands like here? Now here, this is which functional group it is? Like here.
Carbon.
Yeah, it's carbonyl. So carbonyl stretching will be at, and carbonyl it's
3000.
3000. No, you like in IR carbonyl stretching are generally approx near about of 1700.
Yes, 1600 to
Yeah.
1690
But
to
it depends
1700.
whether it is ketone or aldehyde or ester. So it will vary. So now it is ketone. So like for ketone, the stretching frequency will be near about at 1700, and this CS stretching also. So CS stretching will be at 2960 to 2850 centimeter inverse. Now for the ethanol molecule. For the ethanol, there are CS stretching, OH stretching. So we already discussed like OH stretching, it's approximately about 3600. So the exact value will be near about at 3630, and the straight stretching same at 2960 to 2850 centimeter inverse. Now here it is acid, like carboxylic acid. Now, so for that the OS stretching will be at 3030, and like there's carbonyl group also. So the carbonyl group the stretching will be at 1700 to 1750. Now for the D part here there will be CO stretch, and also there is a double bond. So there will be C double bond C stretch also, and sp2 hybridized carbon and hydrogen stretch also. So for the CS stretch, it will be at 2960 to 200 2850. For carbonyl, it will be near about 1700. For C double bond C stretching, it will be at 1650. And for sp2 hybridized carbon to hydrogen, it will be 3040 to 3010 centimeter inverse. Is it clear? So just remember, like for carbonyl, the stretching is approx 1700. Like for OH, it's approximately 3600. And for CS stretching, it will be approx 2800 to 2900. But the value will change depend by the its acid or aldehyde ketone. Now the next question is, give the approximate characteristic absorption band of CN group in the IR spectra of the following compounds: C6H5NH2. So what will be the absorption of CN? It's C6H5, so it's aniline. And here if you will see the nitrogen attached to one carbon, so it's a primary amine. So you know what are primary, secondary and tertiary amines?
Yes, ma'am.
So what's the difference between them?
Primary amine is attached to the primary carbon, secondary amine is attached to the secondary carbon, and tertiary is attached to the tertiary carbon.
Or you can just say, like, if a nitrogen attached to one carbon, then it's primary. If it is attached to two carbon, then it is secondary. And if it is attached to three carbon, then it is tertiary.
Yes,
Like,
yes, that can also be there.
yeah. So this is aniline. So this nitrogen is only attached to one carbon, so it is a primary amine. Like if you look at this structure, this is diphenyl amine. Here nitrogen is attached to 2-phenyl, pH, pH. Like here it will like this. Like here N is attached to 2-phenyl rings. So basically here nitrogen is attached to two carbons, like here 1 and 2. So this is a secondary amine. It's diphenyl amine. Similarly here triphenyl amine, and it's CH3NH2. So what will be the absorption band of CN in all these cases? So first tell me about this, like phenyl amine or like aniline. So what will the value of the CN's band? Now you know that for primary, secondary, tertiary, the value will be different. Here it is primary amine. So what will be the absorption band of CN group in this? Just tell me a rough range. Vaishnavi, Jyotika, Jasna, Anu. What will be the value? Like for this, it will be approx 1340 to 1250 centimeter inverse. So now here it's diphenyl amine. It's a secondary amine. So so for here, what will the value of the CN group? It's secondary amine. It will be also 1342 1280 centimeter inverse. Now for here three phenyl rings are attached to nitrogen. It's a tertiary amine, like nitrogen attached to three carbon. So here the range will be 1360 to 1310. Is it clear?
Yes, ma'am.
Okay. So what will the value for this CH3NH2? Like for the CN group, what will the value here? Here it is also primary, but it's aliphatic. But here in that was aromatic one. So what will the value for this? It will be a slightly lower value. It will be 1220 to 1020 centimeter inverse. Is it clear?
Yes, ma'am.
Okay, so I will just conclude what we have studied in this session. So we discussed about Raman spectroscopy, that there can be elastic scattering or inelastic scattering, and further in that we discussed about Rayleigh scattering, Stokes scattering, and anti-Stokes scattering. What was Rayleigh scattering? In that, if a molecule is excited to a virtual state, then when it relaxes back to the ground state, then it will come back to its original state. And this type of scattering is example of it, like is a elastic scattering. So here it will be the energy will be equal to the h mu. While in the Stokes scattering, it is an inelastic scattering. What happens in that, if a molecule is excited to virtual state, then it relaxes back to the ground state of low energy level, that to of your original state. So here it will be equals to h minus del E, or like for Stokes shift, we know that if Raman shift is this, then for Stokes line it is frequency of incident minus frequency of scattered. That is for Stokes. While what is anti-stock? In anti-stock, if we excite a molecule to any virtual state and then it relaxes back to a ground state of higher energy, then higher vibrational state than that of the original state, then it is anti-stock scattering. Here energy will be given by h mu plus del E, or like in terms of, if we have to determine by Raman shift, then it will be mu s minus mu 0. Also from the spectra, like the Raman spectra, we know that anti-Stokes line are those lines which are right to the Rayleigh scattering, and the wave number value will be more for anti-Stock, while Stokes line are though that is left to the Rayleigh line, and here the wave number value will be less. So then we discuss the formula or equation of the Raman shift, that is mu s minus mu naught, and the Raman shift of the Stokes line should be positive while that of the anti-Stokes line would be negative. Then we discuss like what will the correct order of the intensity. So the correct order will be Rayleigh, Stock, and then it will be anti-stock line. Then we discussed about overtones and the fingerprint region. So we know that in IR there are like functional group region and the fingerprint region, and in fingerprint region it generally lies in the range of 1400 to 600 centimeter inverse. While what are overtones? Overtones are basically they are as a result of the absorption of light at a higher energy level than that of a fundamental frequency of radiation vibration, and they are generally observed in near eye region. Then we discuss about Hooke's law, that it is, if we just look at the equation, mu is equals to 1 upon 2 pi under root k by mu. So where k is the force constant, or it tells about like how strong a bond is. So if we have triple bond, double bond, and single bond, so the bond strength will be higher for triple bond than that of a double bond and that of a single bond. So in acetylene it's CH triple bond CH, so it has a triple bond. In ethane it is sp3 hybridized at a single bond, and for ethylene it's CH2 double bond CH2, so it is a double bond. So if we compare acetylene, ethane, and ethylene, out of these acetylene has a triple bond, so the force constant will be higher for acetylene as the bond strength is more in acetylene. Then we discussed about aromatic CH stretch, that the aromatic CH stretch ranges from 3100 to 3000 centimeter inverse, and then you have to remember the values for different function groups. Like for carbonyl, it's approx 1700, but it will change whether it will be ester or aldehyde, ketone, or acid chloride. And for OH, it will be near about 2000. Like it will be generally greater than 2000, but it will vary depending if a molecule has, suppose, intermolecular hydrogen bonding or intermolecular hydrogen bonding, so the values will be different. Then we discuss like iron cannot distinguish between enantiomers. Then we just determine the vibration stretching frequency of a CO molecule if the force constant was given. Then we discussed about mutual exclusion principle, that if a molecule has center of symmetry, then IR active will be Raman inactive, and Raman inactive will be IR active, or vice versa. That was mutual exclusion principle only if a molecule has center of symmetry. But if a molecule does not have a center of symmetry, then it can be both Raman as well as IR active. Like we discussed, for the homonucleotidic molecules like H2, O2, and N2, they are generally IR inactive because there is no change in dipole moment. Hence, they are Raman active. But for CO2 molecules, there are three vibrational modes like symmetric stretch, asymmetric stretch, and bending. But in case of symmetric stretch, it is Raman active and IR inactive, while that of bending, it's Raman inactive and infrared active. And for the asymmetric stretch, it's Raman inactive and IR active. Just now, then we discussed about what will the frequency, like whose vibration frequency will more, as we know that in here chlorine, Br, oxygen, carbon has higher mass, but in hydrogen has less mass. So we know that such a frequency is inversely proportional to the reduced mass. So hydrogen has smaller mass, so stretching frequency will more for hydrogen. So that's why option one will be correct. Then we discuss like invert factors the rubber intensity will depend on. So it will depend on intensity of the source, polarizability of molecule, and the concentration of the Raman active group. Then we discussed like how to calculate the frequency of anti-stroke line. For that, you just have to remember two formulas, like what will the value of Raman shift for stroke line and the anti-stroke line. For Stokes line, the Raman shift value is mu naught minus mu s, while for anti-stock, the Raman shift will be mu s minus mu naught. For this question, they have asked about anti-stroke line, so we use the second formula. Then we have to calculate the bond length. So for that, we know that I is equals to mu r square, and bond length is r. So r will be square root of I by mu, and what will the I we will determine from the formula h upon 8 pi square bc, b into c. So h pi b and c we know that. So therefore, by putting the value of I in this equation, we get to know about the bond length. Then we discuss how to calculate the harmonic constant, unharmonic constant, and dissociation energy. So for that, we use this equation omega e into half plus v minus omega e xc into v plus half whole square. So by substituting the values and equating the equations, at last we got the value of omega e xc, which was 11.75 centimeter inverse. And then we substitute this value in any either in this equation and this equation to calculate the value of omega e, and it was turned out to be 2161.5 centimeter inverse. Then we have to calculate the dissociation energy. For that, we know the equation. Yeah, dissociation energy is equals to omega e square divided by 4 omega e xc. From that, we can calculate the value of dissociation energy. Then we discussed about IR bands. So from here, you just have to remember, like for carbonyl, it the value is approx 1700. For OH stretch, it will be approx 3600, and for the CA stretch, it will be approx 2800 to 2900 centimeter inverse. And for C double bond C stretch, it was approx 1600, and sp2 hybridized carbon and hydrogen, it will be 3040. So this you all have to remember. Then we also discuss about the CN group, like it will vary from primary, secondary, or tertiary amine, or whether it will be aromatic or aliphatic. So there will be different values. That's all for today. Is there any doubt?
I mean, B3 we had an assignment, but the options given was like M cube. Uh, so that was given as the right answer, but actually it's M square h square by 2y. So there were two or three options with M cube answer.
I could not understand you. What are you trying to say? Like, is there any like some options are wrong in the assignment?
Yes, in the week 3 assignment, there were the second question. The answer was given as m cube h cut square by 2y, but it is actually m square h cut square by 2y. And there were three options with m cube h cut square by 2i value.
Okay.
So we couldn't figure out which one was the correct one. So it is messed up. There were actually two options with m cube h cut square by 2i, and there was another option with 2 m cube h cut square by 2i. And the answer is given like m cube h cut square by 2i.
Okay. So can you share that question in that discussion forum?
Yeah, I'll share that. And week one also there was a question answer key. There was a wrong question like electrons wavelength is actually greater than photon. I have told you like in the last week,
Yeah, that
and
was correct. Your option was correct. There was like the option was wrong in that.
Yes, ma'am. I
okay,
have
ma'am. So
also wrong.
Actually, I am not setting the assignment. I am just here to solve your doubts, but I will just discuss with sir like that answers are wrong in that. So maybe he will correct it.
Yes, ma'am. You can please share this information with course instructor so that it will be get they will get correct that question or no.
Yes, I will. And about this question that you are telling me, like the options are wrong, maybe just maybe you can write it in the discussion forum or just write in the chat box also, like the question. I will just check it once because actually I am not setting up the assignment questions. Actually, the course instructor is only setting the questions, so maybe I will just ask sir about that, and he will just clarify. Maybe he will just change the option whatsoever will be possible for him. Are there any doubts?
no, ma'am.
Okay, and like, so this question you were telling me, just can you share me that question in the chat box? So you have a basically a
Okay, ma'am.
doubt in week assignment second and third, no? Is there any doubts in week first assignment also? Okay, just like send that question in discussion forum. Thank you. That's all for today.
Thank you, ma'am.